Complex Analysis Lesson 4. We're going to cover roots of complex numbers, the fundamental theorem of algebra, and we're also going to show a solution to a problem that I posed at the end of lesson number 1. Roots of unity. Consider the equation z to the n equals 1 for some complex number z, and n is a natural number, 1, 2, 3. Our problem here is to find the possible values of z that satisfy this simple equation. In the case of n equals 1, there's just the one solution, right? Z equals 1. If you have n equals 2, then you're taking the basically the square root of both sides, and you get z equals plus or minus 1. We know that from just basic algebra. The problem becomes more difficult and less obvious as we increase n. So let's look at n equals 3. The first thing we do is we represent 1 as e to the I 2 pi m, because it repeats, the value repeats. The radius here, the r, is just 1, of course, and the angle is either 0 or 2 pi or 4 pi or minus 2 pi and so on. So that's how we represent 1. And then we rewrite our equation here. Z cubed equals e to the I times 2 pi m. And we just have this here. Now the question is, do we get, how many different values do we get here? Because m goes potentially to infinity, but as you'll see in the next slide, there's only 3 possible values. Okay, so here's our equation from the last slide. Let's put in 0 for m. That just gives us the solution we knew, right? 1 cubed, of course, is equal to 1, so we knew that one. But if we put in m equals 1, then for m here, we get e to the I 2 pi over 3, and then we use the Euler's formula here, cosine 2 pi over 3 plus I sine pi over 3, and we get minus 1/2 plus I times the square root of 3 over 2. If we put in m equals 2, we're basically just getting this angle, except it's in the third quadrant, and so we get negative values for both the sine and the cosine, and you see the solution here. If you put in m equals 3, 4, 5, whatever, you start, when you put in 3, for example, you just get m equals 3, you get just 2 pi, which is 0, and you get this solution again. If you put in m equals 4, you get the same as this one here, and so forth. Okay, this slide here is a bit of a review. It's basically computing one of the, or two of the values we had on the previous slide for sine 2 pi over 3 and cosine 2 pi over 3. So 2 pi over 3 we measure starting from the x-axis and going counterclockwise. The way you compute the sine and cosine when you go out of when you're in the second quadrant is you just take the smaller angle here, which is pi over 3. That's 60 degrees. And just take a value. You can put any value here in terms of this this vector. I'll put in 2 because it's easy to work with. Then you complete the triangle. Just put another leg here and make this angle pi over 3, and then you have 60 degrees, 60 degrees, and of course 60, since you add up to 180. So if this is 2, and this line here bisects the base, then this is a 1. But since you're in the negative x-axis, this is a minus 1. And then using the Pythagorean theorem, you can determine that this value is the square root of 3. And then it's pretty easy. You just have the sine of this angle is the opposite over the hypotenuse, square root of 3 over 2. And the cosine is the adjacent, minus 1 over the hypotenuse. which is 2. So this is how you go about doing this. Of course, if you have angles other than 30, 60, or 45, you get into more complicated computations. But normally for examples, we'll stick to the easier examples. The other computation from the previous slide was 4 pi over 3, and that just brings you into this third quadrant. And you get this same triangle that's just kind of flipped, reflected, I should say, about the x-axis, and then both the x-coordinate and the y-coordinate become negative, and that's how that works. On this slide, we look at the general solution to z to the n equals 1. We write 1 as we did before as e to the 2 pi m. M could be 0, 1, 2, 3, up to infinity. We take the nth root on both sides of this equation. We get z equals e to the 2m pi over n. We use Euler's formula to get this expression. And then we just make a note that as m equals n is the same solution as m equals 0, m equals n plus 1 gives you the same solution as 1. In fact, it repeats, so you're only going to get n solutions here. Here's a drawing of the fifth roots of unity. You can see here you have 1. You're always going to have 1 as a solution, and then these are spaced every 72 degrees, or 2 pi over 5. 5 is the the value of the n, and you can graph them on here. You see there, you get a nice picture. And each one of these, if you take this to the fifth power, you'll get 1, which is pretty obvious here because it's in exponential form. So you can see that you're just going to take any of these to the fifth power, you're going to get e to the even number times pi I, which is 1. We could also take the nth root of a complex number other than 1. Here we have z sub 0 equals r e to the I phi. R is the modulus of z sub 0, and phi is the angle z sub 0 makes with the positive x-axis. And that'll repeat every 2 pi. So we basically have this equation here, z to the n equals z sub 0 equals r e to the I times phi plus 2 pi m. We take the nth root on both sides. We get z equals the nth root of r e to the phi over n plus 2 pi m over n. And we can rewrite that in using Euler's formula, as you see here, in terms of the cosine and sine. And as m goes from 0 to n minus 1, we get different solutions. But once you hit n, you start repeating. When you put in m equals n, you get the same solution as m equals 0. And if you put in m equals n plus 1, you get the same solution as putting in m equals 1, and so on. On this slide, we have a diagram from Wikipedia. I've given you the link here in case you want to go to the source. In fact, there's some good information on this article from Wikipedia. It's called Root of Unity. And as I say, this is one figure from there. So they start with a complex number, z equals r e to the I phi. And you see phi is the angle the complex number makes with the real axis. In the previous slide, we used z sub 0 just to kind of give you a perspective. And where we use z, they're using x. I don't know why. Normally you don't use x for a complex number, but they did. So the first one here, and I'm not going to go through all these, but they go through a few of them. The first one here on the right, upper right, you see here it's basically the square root of this complex number. You have the square root of r, and then you have e phi divided by 2, and then you have another one symmetrically across, basically 180 degrees on the other side in the third quadrant. And r, they even show like the outer, this is the same r here that you started with, and this is the square root. So if r is bigger than 1, of course it will be smaller, but if you had r equals, say, something like 0.64, then the square root of that is 0.8, which is bigger. So this is just a general figure. Here you have the cube root. You see that's the phi divided by 3 is where you start. And you have the cube root of r as the modulus. And then you have the other two roots basically 120 degrees separated. For the fourth root, you start with phi divided by 4. That's the first one you get. And then they're equally spaced, basically 1/4 of 360 or 1/4 of 2 pi, 90 degrees apart. And the ones for 5 and 6, I kind of get a little bit overworked here, but it's the same idea, right? You start with one complex number, and then they're 1/5 of the circle, 1/5 of 360 apart, and then 1/6. And as you get into higher roots, you get the same pattern. On this slide, we have an example of taking the third root of a complex number. First step is we just write the complex number in polar form. So we have -1 plus the square root of 3. This should ring a bell since we had derived it a few slides ago. We know it's 2 times e to the 2 pi over 3. We take our general formula and we plug the numbers in. We have the r, in our case here is 2. Put in r equals 2, and then the angle phi is 2 pi over 3. And plug that in here. And then we know that in the case of a third root, there's only 3 different solutions. So we just cut it off here at 2. You can put in m equals 0 and get this first expression. M equals 1 gives us the second. You need to do a little bit of addition here for the sine and cosine. And then you put in m equals 2 and you get the third solution. And you can write 14 pi over 9 as -4 pi over 9. It's just going in the clockwise direction if you use this expression here. If you go in the counterclockwise direction, then it's this one here. The fundamental theorem of algebra. If you have an equation in complex variable z to the nth degree, so as we've shown here, and then your coefficient zn is not 0, so you know that it's an nth degree equation. There's exactly n roots. They may be repeated, but you always have n roots when you're looking at the complex numbers as the possible solutions. If we know from algebra, actually, if you have a real equation of degree n, you may not get n real roots because some of them are complex. So the theorem formally stated is listed here. There's 2 parts. One part says you have at least one complex root. That's not all that easy to prove. It's a bit complicated. We'll give a reference to that. The second part can be proven using the first part, and we will prove the second part of the theorem, which basically says you can factor the polynomial in terms of its 1 degree equation, z minus c1, z minus c2 up to z minus cn, where the c1 to c2, cn are the roots, and a is just the constant. Okay, as I mentioned, the first part of the proof is not going to be proven here, but it can be found in the Wikipedia article, Fundamental Theorem of Algebra. Assuming that's true, that there's always at least one complex solution to an nth degree complex polynomial, we'll go ahead and show that you can factor the polynomial as we showed in the previous slide. If you let c1 be that one root, then you can write p to the, using long division, you can write our complex function here, pn of z, the n kind of meaning nth degree. We have pn of z equals z minus c1 times pn minus 1 of z plus c, where pn minus 1 is an an n minus 1 degree polynomial. However, we were told that, or we assumed C1 was the root. We were given that. So if you plug that into this equation, you have P sub n of C1 equals 0, and you're putting in C1 here. This is going to cancel, right? You're going to get 0 here. And this on the right side gives you C. So C equals 0. And we basically can eliminate the constant, and we just get this equation here. All right, just taking our equation from the last slide here, the first line, that's where we had stopped. You can probably see what we're going to do. If this Pn minus 1 is an n minus 1 degree complex polynomial, our first part of the theorem tells us there's at least one root. We'll call that C2. We can factor that out of Pn minus 1, and we get this part here. This Pn minus 2 is the second n minus 2 degree polynomial. There is a potential constant, but we can show that that's 0 just the way we did before. And then we continue the process. Eventually we run out of degrees, and we just get the whole thing factored here. P to the n z equals a constant times z minus c1 times z minus c2 times z minus cn, where c1, c2, cn are the roots. And just note that they can be repeated. For example, if our p to the n z was, say, 3 times z minus 3i to the 7th power, then 3i would be the root, and it's repeated 7 times. You may recall I posed a challenge at the end of lesson number 1. We had this quadratic equation, and the challenge was to find the roots. And if you got it, congratulations. It wasn't an easy problem. What you do is, we'll solve it here in case you hadn't solved it already. What you do here is you can use quadratic equation. So you have your your minus b here, plus or minus a squared minus b squared, minus 4ac divided by 2a. Plug all those things in. You can simplify a little bit, and you get this expression here. So we know what all these things are, except we're kind of stuck here, right? Or at least up until now, we didn't know how to find the square root of minus 14i. And we kind of got two of them. We got the plus or minus out here. So we can just find one of the square roots and then plug it back in, and we'll have our solution. So continuing, the problem reduces to finding the square root of minus 14i. As before, in our other example, we write the complex number in polar form. The modulus is 14, and the angle, if you think about it, it's minus 14i. That's minus pi over 2. It's sort of the negative imaginary axis. And so we take the square root of that, and we get the square root of z equals square root of 14, e to the minus pi over 4i. And then you put in the minus pi over 4i and using Euler's formula, which we have here. You can compute the cosine of minus pi over 4 and the sine of pi over 4. You plug that into your equation here, and you get this. And you notice that you can write the square root of 14 is the square root of 2 times the square root of 7. So when you multiply that through, the square root of 2 times the square root of 2 gives you 2, which cancels with the 2 here in both cases, and then you just get this expression here, which is almost what we need. We just need to plug that back in here to our formula. So we put this in here, get this, and then the last step, we just take the plus and then we collect the real part and the imaginary part, and we write it this way. Then we take the negative of this, and again we collect the real and the imaginary parts, and we have our solution. On this slide we have some exercises. The first one is to find the third roots of z equals 8i. I provide the answer here, and I confess I use ChatGPT to check the answer. The second one is to find the roots of z squared plus 2iz minus 1. It's a repeated root and it's minus I. You can either try to factor this or use the quadratic formula. Third problem is a bit messy. Find the fifth roots of 1 minus I. I used ChatGPT. It actually gave a very detailed solution. I was impressed. If you just type in what I have between the quotes here, leaving the quotes off, hopefully you'll get the same answer I did. It was, as I say, quite remarkable that it was able to do that. All right, that's the end of this lecture. Next lecture we'll be getting into complex functions.